Well, welcome back. We're nearing the end of our syringe robot arm excavator project, and today's project is to build one of the very final elements that we need, and that is going to be the bucket for scooping up the dirt out of the pit. Before we get to building the bucket, though, let's take a look at what we're going to need to think about before we start building it. And I've started almost all of the videos with a little snapshot of a drawing. And I do have a sketch of where we're going to go with this, but I think it's important for us to take a moment and actually do a calculation, or at least think about the calculation that we do before going in to start generating our bucket. And the big question we want to answer right now is how much am I going to be able to lift with this arm? Okay, and oh, singe. Obviously, I don't have spell check in my pen. Okay, but let's take a look at what this arm is going to be doing in here. Okay, so our arm's right here, and our bucket's going to be out at the end of the arm. And when we reach down into the pit, that bucket has to be able to pick things up, pull it out. It's got to be able to lift the dirt. And then we've got to be able to extend that arm out to right here and lift that all the way up. Now we've got one syringe right here pulling this in order to extend this arm. And we've got this weight out here. And I think we're going to be okay for this syringe extending, and it should always compact okay because it's always going to be under compression. The 30 milliliter syringe should have no problem generating enough force to push this entire assembly up. We've got a nice long lever arm right across here. But I am a little bit concerned about the 20 milliliter syringe, that if we have too much weight out here, that we'll be able to get it to go down no problem, but then we won't be able to get it to pull back up. And so we want to take some of the calculations and concepts that we took a look at earlier in the semester where we were talking about moments and apply it to solving a problem for this arm. And in order to do that, we need to be able to do a couple of things here in Fusion. Now, let's just pull this back and take a look at this from a two-dimensional perspective. And to get a nice view square onto this side, you can always use the look at tool right down here and look at. If you click on that and bring it up and pick a face that you want to look at, that will spin things around so you can look exactly at the face that you're looking at right here. And you can see that right in here, we have this syringe pulling this in right here. Okay, now we need to know a few things about the syringe, and we've got measurements and we've done calculations on the syringe before, and it's got about a 10 millimeter inside radius on that 20 milliliter syringe. Just happens that the 20 milliliter volume syringe happens to be about 20 millimeters in diameter, which gives us a 10 millimeter inside radius. Take pi r squared to get the cross-sectional area that the syringe is activating on. 3.14 times our 10 millimeter radius squared gives us 314 square millimeters at the end of that syringe. Now, keeping in mind that the syringe is going to be retracting, we spent some time talking about how syringes actually work and how hydraulic cylinders actually work. And because this is a single acting cylinder, we've only got liquid on one side of it. We don't have liquid on this side. In a real excavator, you'd have liquid on this side pushing this plunger back. But out here, we've only got atmospheric pressure coming down to press this plunger back in. And that means that we've got some real constraints on how hard we can pull on that syringe before we start to get bubbles starting to form in our water. So let's come back here, and we know that atmospheric pressure is about 100 kPa at sea level. If you're at higher altitude, of course, you're going to have problems. And if you're up on top of Mount Everest, this syringe arm probably won't work at all, most likely because the water's frozen and because you've just died of lack of oxygen. But at the rest of altitudes, we should be doing okay. So 100 kilopascals is the equivalent of 0.1 megapascals. And from earlier in the year, we've used this megapascal term in tension and compression calculations. And we know that since a pascal is 1 Newton per meter, a megapascal is 1 Newton per square millimeter. So there's a million newtons in a megapascal across one square meter. So there is 1 Newton across a square millimeter, which is really handy because it lets us say that there's about zero 0.1 newtons per square millimeter of force acting on everything due to atmospheric pressure at sea level. Now, take this to your chemistry teacher, they'll tell you, oh, no, 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 no. Sea level standard temperature and pressure is 101.3 kilopascals at 23 degrees Celsius. If they do that, smile, nod nicely, and back away slowly. We're rounding some numbers off here to get a rough idea. And, we're ballparking. And it's a lot easier to do the math with 100 kPa than 101.3. So anyways, here we go. If we've got 314 square millimeters, oops, why didn't I put a square in there? That definitely needs a square. There we go, I've got the square in that one. Times 0.1 Newton per square millimeter. That should give us 31.4 newtons of pulling force as an absolute maximum. Now, keep in mind that if you've got dissolved oxygen or dissolved gases in your water, those gases may come out long before you reach this point. This is just the absolute maximum possible pulling force that you can get from this syringe. Okay, all right, so now let's take a look at how this works out on our arm. So we've got a pivot point on our arm right here, and I've simplified a little bit, moved this up to a nice 90-degree angle so that our math works easier, but I've sort of fudged on the length right in here. So again, we're roughing things out. When you do your calculations, so long as you're reasonably conservative and you don't need to calculate to the nearest significant figure, you can make these approximations to give you an idea of what's likely to work. All right, so we've got 30 newtons of syringe pull activating right back here. That's going to give us a moment pulling backwards of 30 newtons, and it's going to be activating at about 50 millimeters. Well, where did I get that 50 millimeters from? Well, I came into this drawing right here, and after doing the little look at right here, we've got this really neat measure tool under inspect, and I was able to come down here and pick that surface, and oops, that's telling me 75 for some reason. That's going diagonally on there. I don't know why it picked that. Let's just close that and try that again. I think it gave me the wrong surface because I was just looking at the 2D perspective. And right in there, and I'm not quite sure why it's giving us that blurry figure. 58.6 is the number that pops up right over here. Now, like I say, that's 58.6 right there, but really that's going to be actuating at a distance right in here. And so I round it down just to be safe because, like I say, when you're estimating things, always estimate on the conservative side. So I said it's going to be 50 millimeters. Now, we need to know how much the arm weighs because going in the opposite direction, we've got our syringe pulling it down this way. We've got our arm pulling it down that way, the dead weight of the arm, and we've got our bucket pulling it down this way. And we can use the same tool to figure out what some of these numbers are going to be. So if we come back over here, we can come in here and we can do, let's just close that and start a new measurement. Let's do an inspect. And we've got the measure tool up. And we can do a measure from right there out to right here. This should be 230 millimeters. That's giving us 236. Okay, I can live with that, whatever is. Again, I've rounded it to 230 to make the math easier. And that's where our bucket is going to be mounted. We're going to assume the entire weight of the bucket is right out here. We're also going to have the weight of a syringe in here, and the syringe is going to sit somewhere between right here and right here. We'll estimate that distance in just a moment. Let's take one more measurement and come in right here. And what I want to measure is the measurement to this little point right there. Now, what's that point? Where did it come from? How did I get it? Okay, so what I did in order to get that point was I took this piece right here, and you can see I've trussed mine out. If yours isn't trussed out, you're going to have a different mass, and it's going to be a different place, and that's okay. You'll see here why I think trussing this out makes a difference. I was able to get rid of about half the mass by trussing that out. But let's come in here and arm linkage arm right there. So find the object that you're looking for. And if you've assigned it a material, right click on right there. And what we'll do is we will pop this up and let's take a look right here at properties. Okay, and properties right here, it's going to give us the mass of this part, and it can give us the mass because it's calculated the volume of that part, and it knows that it's made out of MDF, and it knows the mass of MDF, so our part is going to weigh 48 grams. Of course, I've rounded that off to 50 to make our math go a little bit easier. Now, the thing that we want to know is where is the center of mass for that? The point where this would balance. If you could balance everything on a pinhead, where would that pinhead be to make everything balance? And that's what this little glyph, as they call it, is for. And if you come up to inspect, right in here, you can pull up center of mass. So if you've got an object selected, just come in here, tell it show us the center of mass, and you could pick the center of mass for any object right in here. So for instance, if I needed to know the center of mass for that arm, I just say OK right there. And for some reason, it gave me the center of mass out there, which doesn't really look like where the center of mass for that arm would be. Oh, that's the center of mass for the two combined arms. Pardon me. Let's get rid of that. This is the center of mass for just this one arm right here. And so you can measure the distance to that. And let's just go inspect. Pick that hole right there. That's the point everything's pivoting about. And come out here and move this around so you get the center of mass. Now that's telling me 90 at a bit of an angle. And I think for my calculations, you'll see that we rounded that off again. And in this case, we rounded it up to 100. So we rounded the mass up of the arm to from 45 grams to 50 grams, which comes out at 0.5 newtons. We rounded the distance up a little bit to 100 millimeters. Again, not huge rounding up, but if you're going to round somewhere when you're estimating these things, here, this is good. This is working in our favor, so I tend to round down. And here, this is bad. This is working against us, so I tend to round up because you want to keep your estimates conservative. Because if you do it the other way, you're likely to get to an answer that doesn't actually work out. And then I also estimated the syringe mass, and the 10 milliliter syringe we have out here, its mass is going to be primarily water. And so when the syringe is fully extended, a 10 milliliter syringe will have 10 grams of water in it. And I said, it's probably about 150 millimeters out here. It's fairly light relative to the overall structure, but anyway, we'll give it a value. Now, the other thing in here that I'll notice is you'll notice my arm's coming in at 45 grams, rounded up to 50, whatever. And that's okay. If you didn't truss out your arm, it probably weighs about twice as much. That's also okay. You can see when we do the calculations that you just won't be able to lift as much in your scoop as a result. Okay, so now we've got a little bit of a calculation in here. Our bucket mass is sitting way out at the end, and we don't know what M is. We want to solve for M. So 30 newtons times 50 millimeters gives me 1,500 newton millimeters, pulling up that way. And from that, we subtract our arm mass times the arm distance, our syringe mass times the syringe distance, and our bucket mass times the bucket distance out at 230 millimeters way at the end. We go through, punch all those numbers into the calculator, and it comes out and tells us that we might, if everything goes perfectly, have our absolute maximum load that we could lift out at this end, 6.2 newtons. Okay, so about 600 grams, which is a lot. That's, like a I don't know, 2 pop cans or something like that. That's a pretty heavy load. I don't think we're actually going to be able to lift that much. So what do I do with that number? Well, I say, well, our bucket plus the load, could weigh 620 grams maximum, but I really doubt it. We've got things to overcome like the friction of the plunger inside the cylinder. We've got the friction between the arm and the boom. We've got the chance that something's a little bit sticky or not perfectly lined up or not working perfectly. So we're going to add a safety factor. Now it depends what you're adding for your safety factor and how brave and bold you are. So I think it's reasonably conservative, and you can probably fairly say that if your your bucket plus its load weighs 300 grams, then you're probably going to be fine for what it is that you want to lift. If it weighs 400 grams, you'll be working and you might start to see some bubbles starting to form in your arm, but you can probably get it out there, and maybe you just don't take as big a scoop every time. And if you go up to 500 grams, well, you're probably pushing it. If you go to 600 grams, I'm pretty sure that's not going to work. Okay, so it depends. If you're feeling fairly conservative, make a smaller bucket so that you've got a smaller load and a lighter bucket. And if you're feeling bold and you want to go for it, make a bigger bucket. You can always make another bucket, because I'm going to show you how to make the bucket in just a moment. And as you'll see, it's very parametric. It's very easy to change, and we've got a couple of techniques that make the bucket fairly easy to manufacture. Okay, now as far as your load goes, we are going to be lifting up plastic to represent dirt. And again, making ballpark estimates, our plastic has a density of about 1. So 1 gram per cubic centimeter, 1 gram per milliliter, 1 kilogram per liter, however you want to phrase that. How we know it's got a density of about 1 is because they kind of sort of float, but not really well. Now, this is a little bit of a high estimate because we're going to be lifting plastic pellets, and there's going to be void space in between the pellets. And yes, there's formulas. We can go and calculate all that and estimate that. In fact, the ideal thing to do would be to take a beaker and take some of the plastic pellets and actually weigh how much 300 milliliters of the pellets weighs, or something like that, to get an actual mass of the pellets when they sit in your scoop. But I'm just going to use 1 gram per cubic centimeter right now, because that seems to work. And this would also work out to be, if we were talking about per cubic millimeter, remember when you go from a cubic millimeter to a cubic centimeter, it's a factor of 10, but it's 10 cubed because you've got your height, width, and depth that all need to be compared. So you'd have 1 milligram per cubic millimeter. Ooh, got all my metric conversions done in my head right there. Okay, now we do have some options that if you make your bucket just a little bit too big, what can you do? Well, keep in mind that one of our problems right here is, where did that arm go? Is that the retraction right here is only being driven by air pressure right now. If you put some elastic bands between right here so that this is always under compression and the elastic bands are pulling in, then what you'll do is you'll press on your syringe to extend it. And you can do that to a much higher pressure because you'll have fluid trapped inside here, and you don't have to worry about the gases coming out of the fluid as you press it at a higher pressure. Plungers, syringes, cylinders always work better when the fluid is in compression and you're pushing something out, because you really don't have the option of putting it into suction. There you're just relying on air pressure. So if you were to have some elastic bands between right here and you got your elastic bands balanced just right, you might be able to get more force for retracting this and extending your arm right here. So you can probably go bigger if you build a bigger arm right in a bigger arm. You can probably build a bigger bucket if you use some techniques like that. How big? It kind of depends on how good you are at hooking up those elastics and balancing the forces. So you've got some of that in there. And keep in mind that we're going to show you ways to make this bucket that are pretty easy and quick to do. So you might have a couple of different buckets. One is your regular everyday practice bucket, and then the big one that you go to for competition. Just as a ballpark, we're going to take a look at the 3D printed ugly bucket. That's going to be the first design that I show you. And then I'm going to show you a sheet metal design. And that 3D printed ugly bucket, when it's all done, Fusion estimates its mass to be 100 grams. It's going to be less than that after we run it through the slicer because the slicer then takes care of the infill density. And if you've done some 3D printing before, you'll recall that we don't actually print solid objects when we print in 3D. We give it an infill density. So our bucket mass is definitely going to be less than 100 grams. One of the interesting areas where parametric solid modeling programs are advancing is in how they model 3D printed parts. And some of them now are starting to do the slicing inside the program so that they can actually give you the final printed part and then its properties. And you can come back and do your finite element analysis and your mass analysis all based on the part as it's actually going to be after it comes off the 3D printer. Those are new features that are rolling out in different programs right now, and I'd expect you'd see them being pretty standard in the next 5 years or so. Maybe less. Autodesk is really pumping resources into Fusion 360. Finally, we also know that the volume of that bucket, and I'll show you how we got this information, is going to be about 172 cubic centimeters. So there we go. If we've got 172 cubic centimeters of volume at 1 gram per cubic centimeter, plus 100 grams right there, we've got like a 270 to maximum gram weight out at the end of our arm, and that's just under the 300. And the interesting thing is I designed this just sort of based on ballpark estimating and experience and having seen a lot of these arms. I said, yeah, that kind of looks about right. And in here, I actually came along and did the math and said, I think this is probably somewhere that's going to work okay. So there's certainly advantages to being able to do the math to confirm this, but there's also advantages to having practical experience and empirical knowledge of how these things behave. So let's start looking at how we might go about creating that bucket. And to do that, I've got another picture right in here that shows some of the ideas that I had when I was putting the bucket together. Okay, so I was looking at two different ways to do it. In my first design, I was thinking that a sheet metal bucket might be the ideal way to go about doing it because that gives you nice thin walls and it would be fairly easy to build a sheet metal bucket. You've got a couple of different ways you could fold things up. So you can see that I was saying this side right here could be folded down from a piece right here. This side could be folded down from right here. This side could fold down from right here. That could come right around there, and you could get this all down into basically one piece of sheet metal if you designed it correctly. And you'd have a nice clean edge, thin walls, so all of your volume could be used for holding dirt, as we call it. And so that's not a bad idea right there. Then I was trying to think, well, how do we hook it up into our overall mechanism? And what we've got right here is a couple measurements that we already know. Now, if you've got a slightly different design on your arm, that's okay. I'll show you how to get those measurements in just a moment. But from outside face to outside face, we're going to want 38 millimeters on my design. And between the holes, we're going to want 40 millimeters. And after a bit of playing around with it, I discovered I drew these way too low to the bottom and that this would have ended up jamming into the arm. This actually needs to come up somewhere around here to about 20 millimeters off the bucket so that there's room for everything to flex and move back and forth before this part jams into the arm. So where am I getting those measurements from? Well, as you might have guessed, from the measurement tool. So right over here, we can come in here. Let me close this and start a new measurement. And if I come in here and pick the inside right there and the inside right there, I've got 38 millimeters on the inside. So if you've got a different design on your arm and you want to go for a different measurement in there, that's perfectly fine. And let me close that. And for the distance from right here to the end of the bucket to make sure it all works really nicely, I went back and took a look at our arm end linkage model, the one that we did all up nice and parametrically, where I've got a bucket in there that rotates around. We're going to be able to play with those dimensions a little bit if things aren't working out perfectly. And what's really cool is since you've got those measurements, you don't need to have the rest of the arm modeled. So if you've been struggling with some of the joints and the rest of the arm or all that, you can just take a deep breath. This one's going to start out absolutely fresh. So I'm going to show you two ways to make a bucket. One's going to be out of sheet metal, and the other one's going to be on a 3D printer, because I think they both offer some useful approaches and some neat ideas. So let's take a look right here. This is my 3D printed solution right here. And looking at that, why do I say this is my 3D printed solution? Well, we've got a couple of different. Just a minute, I've got to activate my 3D mouse here. For some reason, it always works better if I give it another command first. Okay, so when I originally designed this, I was thinking that we would end up printing this in this direction right here, because we'd have a nice flat base down here to be our bottom layer that would stick to the print bed. And then you'll notice that my angles right here never exceed 45-degree angle. In fact, I purposely chose them to be 45 degrees right there and right there. And so long as I don't make those angles too steep coming out this way, you can always print the next layer in your print just a little bit beyond the layer on top of it. So we should be able to print this entire model without needing any support material, because this side here also comes up at a 45-degree angle. You might see a little bit of things dropping off right in there. Now, after I've looked at it a little bit more, I said, oh, well, this is no longer our biggest surface. I had to come up and modify this top part. This would also print really nicely this way. And so you can put that down on the bed, and there we go. There's a 45-degree angle right there. Or what I'm now wondering is the best way. No, that's not going to be the best way to print it right in there, because we're going to have that big flat surface right up at the top. And you need a really good slicing program to be able to knit this top part together when it's unsupported on the bottom side. So anyways, we've got two different ways that we could print this and make it come together. I'm starting to think that one's kind of nice, but this was my original thought. And, you could probably, oh, no, if you do it that way, you've got a problem right in there. So we've got a couple different ways that we can 3D print this shape. Let me take a look at this and show you how I put it together, because it uses a new tool that you haven't used before, and I think you'll really like it. It's quite cool. So let's come down right here, and I'm going to use the history timeline right here. Seeing as how I've already made this part, I can just drag my history timeline back here, and whoop, that's like I never did any of those things, but it still remembers what those steps were. They're there and they're waiting for me to activate them. In fact, you can come back to the beginning right here and you can press play, and it will animate the construction and how it all comes together. All right, so let's take a look right here, and let's take a look at that first sketch that I put together. And where did that sketch go? There we go. So all I did right now was I took a look at the profile, and you'll notice I didn't worry about that part that's going up on the top right here. I just looked at the dimensions of the bucket, and I said, well, how big do I want the bucket to be? And honestly, I just ballparked all this because, you can come back and change it later if you need to. But the one thing I did make sure that I did was that when I was dimensioning, I used my dimension tool right in here to dimension this angle right in here to be 45 and this angle right here to be 45. So those parts were in there. This one's a 90-degree angle, meaning this is coming up at 45. So I've got a shape that looks something like that. Now, later on when you're all done, maybe you want to fill it a corner or two to make it look a little less ugly. But you know what? 45-degree corners work. Certainly for getting all of your angles right. Okay, so what I did then was I finished my sketch, and I just had that two-dimensional profile, and I applied an extrude to it. And now I've got this one solid block right in here. And this is where I came in and I said, okay, just a minute before we go too much further, give it a second here. I'm supposed to see my body right here. There we go. And I just took a look at that and I said, what are my properties of that body? Oh, I've already assigned plastic material to it. So that's telling me that if this was a solid piece of plastic that size, it would be 164 grams. Okay. The other thing it's got is the volume right here. Now you'll notice this is in millimeters cubed. We want this in centimeters cubed or milliliters. So remember what I was saying, you've got a factor of 10, but a factor of 10 in height, width, and depth. Okay, so that means 10 times 10 times 10, you've got a factor of 1,000. Well, this is 1.7 plus e to the fifth plus 10 to the fifth cubic millimeters. So we got a factor of 1,000. So we subtract 3 right here. That gives us e plus 2, which means we move the decimal place 2 spots over, 172 cubic centimeters. Okay, so that was where that volume measurement came from. Now, this is the tool that you probably haven't used before, and it's pretty cool. It's the shell tool. And you'll notice that just suddenly vacated on the inside right here. So cool. What did I do right there? Well, there is this create tool right in, or sorry, modify. Actually, there it is right up at the top. You click on shell, and when you've got an object in here, shell will come in and you tell it which surfaces you want to remove and how thick you want the wall to be. And it will go through and it will remove everything else and just leave the shell of that object behind. So really, really useful tool, and it completely changes how you can design a hollow object. You don't have to design it with thin walls to begin with. You design the outside of the object and then you say, make it 3 millimeters thick, please. You just have to remember that you do have to be able to give it an opening of some kind right in here, which is ideal for our bucket because it removed this face right in here and just made everything else 3 millimeters thick. So that shell tool takes our solid object and hollows it out for us. Now, you can play around with your inside thickness. That's the wall thickness right here. Right here, it provides a uniform wall thickness all the way along. And I went with 3 millimeters. That's about 1/8 of an inch. Probably a little bit of overkill, but you don't have to worry about that breaking. You could probably take it down to 2 millimeters if you wanted a slightly lighter bucket. Okay, there we go. Everything just got a little bit thinner. If you wanted a slightly lighter bucket, and then you'd also have slightly more room for your dirt on the inside. Would I go all the way down to 1? Probably not all the way down to 1. But again, it's easy to try and easy to print one out. So when we get back to the shops and you've got a chance to get on the tools, you might choose to do that. So, okay, there we go. We've got wall thickness right in there. Just updated that. And then once we had that wall thickness in there, I came along and created a new sketch because I needed a place to put some holes. Now, this is different dimensions. This was a bucket that I used in my sheet metal design, and there I had to keep the boom and the arm a little bit wider because they had to be able to be bent on the box and pan brakes that we had at work. With the laser cut stuff, we've been keeping it narrower so that it's smaller and lighter while still remaining nice and stiff. So you're probably going to want to draw a box in here and get it dimensioned. You can see that I've got the overall dimension right in here. So what I did was I came in and I took a dimension from here to here, and that gives us what's called a driven dimension. You can see that's in brackets right there. When you go to create that dimension, it'll probably give you a warning on that. You may, in order to make that, need to do a project, and you'll come down in here and you can do a project of it'll project that entire surface down there, and then you've got all of these lines in here for making your dimensions. And then I said, okay, well, I wanted my box to be this wide. I was careful to make sure that I went front edge to front edge. You don't have to. You could move it back a little bit. You can play around with that. Just make sure you dimension it so it's in place. And then this one right here, I got a little bit tricky. And you can see that I said, well, I want the dimension from that wall, okay, from right there to the outside edge to be 80 minus this width divided by 2. So what that means is that automatically centers everything for me. So let me just escape out of that. So now if I want to take that down to the 38 millimeters that we need to match our laser cut design, I change that from 55 to 38. And on mine, now it says, well, 80 minus 38 divided by 2 is 21, and it automatically centers it right in here. Okay. There's use for all those math classes and thinking about things mathematically. Let's just finish that sketch right there. And then, of course, now I've got a sketch on there. The next command I did was an extrude, and that popped that up to the top. Now this is starting to look like my bucket, and it's going to be able to come in here and pivot back and forth. I just need to add a couple of holes. So I run the hole command. Oh, let me pull my timeline over one more step. There we go. And if I click on that hole command, remember that you pick the face that you want the hole on, give it a couple of references, and then down in here, you tell it how big you want the hole to be. And I went with our standard hole for this project, a 4 millimeter diameter, about the right size to let a number 8 machine screw slide through nicely. Okay, so there we go. There's one hole, and then we'll add the other hole in right here. Now we've got 2 holes right in there, and this project is finished, and you have a nice little bucket that you can take into your design and you can mount in there, and your linkage will come down and connect to right here. Your arm will connect to right here. You'll be able to pull things up, scoop and hold, and dump them out. Can you make it bigger? Yes. Maybe you want to make it bigger by making it longer in this dimension, maybe deeper in this dimension. Maybe this part right down here comes down a little bit further. Just watch your angles and make sure that you always come up with a 3D printable angle. Perhaps you want to get a bit more space. You could draw a sketch right in here and punch that out to the inside. Just so long as you keep it all 3D printable and think about how you're actually going to manufacture that, should work out fine. Radius off a couple of corners. Okay, we've got the fillet command for that. Can make this look a lot nicer. Just remember, if you fillet that inside corner right there, that's going to make this a little bit wider and may interfere with the arms, with the sides of your arm that are going to be coming right down in here. Okay, the bucket is a standalone project. You can build the bucket, it goes into your parts list, and then when you're ready to add it in, you can drag it in right here and you can add it to this component. But if you're still working on this, don't panic. You can build the bucket. I'm going to be back in just a minute. I'm going to show you how to make it out of sheet metal too. So if you've got the bucket all made up for a 3D printing file, that's perfectly fine. We've covered how to export an STL in previous files right here. I just want to take a look at how I'd go about designing the sheet metal variant of this arm, or of the bucket. And one of the things that I'd like to do is, you've often heard me say, is I like to start with a sketch, just so that I've got some idea of what the measurements are going to be. And you don't always have to start your sketches blind or from new. One of the things I like to do is combine the currently printed CAD output that I have with the object that I want to draw onto it. So I just wanted to quickly review how to get a drawing from your project right here. And so I've reopened just the arm right here. Okay, so you've got this file in your list of parts, double click on that. That pops open and you're just looking at the arm. And what we're going to do right here is we're going to come up to the design and we're going to drop that down to drawing, and we're going to say we want the drawing to come from the design. And when I do that, it's going to ask, what part do I want? Well, it's this one right here. We're going to create a new drawing in right here. And it's going to ask you some things about the template and the drawing that you want. Most critically, which is what size paper do you want to put it on? And A4 is the closest approximation we've got to standard letter size paper. And you can choose it in either a wide format or a tall format. And I believe this is one's going to get me the wide format. If not, I can come back and do this again. But let's go for A4. It's all in millimeters. And here there we go. It should have, there we go, popped up, and there's the wide format drawing. Okay, now you're going to be able to place your part in there in the base view, but we want to adjust that scale. So the scale is at 1:1. And that is just barely going to fit in there. It's not going to quite fit inside all the boundaries. And fact of the matter is, I want to leave a little bit of space at the end for doing some drawing. So I'm actually going to place this over here, not necessarily where I'd be putting it. If I was printing this out as an actual CAD drawing, I'd probably print it out at half scale so that it fit nicely on there. But I want this 1:1, and I want that bucket to be able to fit right in there so I can get a good idea of what it's going to look like when it's sitting right on that arm. So I'm just going to plop that in right there and say, okay, there's my base view. Okay, and you'll see that it does a really nice job of putting the base view in there. Shows you the little sections we've cut out for putting it all together. And that's fabulous right there. Now you've got all sorts of other things down here. You can go in and you can edit your title block. You can delete the borders if you don't want borders on your drawing. You can delete the title block if you don't want the title block. Probably not a good idea to do that in general, but for what we're doing right now to use this as a basis for sketching and get some dimensions, this is probably going to work out a-okay. So I'm just going to print that out now, and I'll be back with the next step in just a moment. Okay, I printed that out and then sketched a potential bucket design in on right here. And I think when there's so many ways to build things in Fusion 360. And just as you need to know how to use Fusion 360's tools, you actually know how to build things in the real world. Because my original bucket design over here, you can see I was thinking, I can make this out of one piece of sheet metal and I'll fold it here and I'll fold it here and then I'll fold it down the back. Then I can have a fold right here. That'll come around to the front. I'll put a couple flanges on. I'll fold them in and it'll all fold together. I'll cut some, and I'm just like, that's going to be miserable to make because unless you've got the right sheet metal tools for making all those bends eventually overlap on top of each other. And it's not a problem to make that if you've got the right tools set up and you're ready to do that nice and easy. But I thought, well, I'm just going to take a look and maybe there's a way I can make something that's a little bit easier to manufacture. And quite often with sheet metal, if you can break something down into a couple of parts, then the bending becomes a lot simpler. So here you can see I've got a piece coming down around the outside, and pop rivets coming through right here, flanges folded up right on there, and then an internal part that's going to have a bend right here and go right across the top. And so, this is roughly what I'm thinking this is going to look like. Part A right here is going to come down the back. There's those three bends with the flanges coming up on there. Part B is going to be the top piece right here with those two coming down on the sides. And then part C is going to pop rivet onto the top, and that's going to provide my connection to the arm. So let's go in here, and I think what we'll do to design this is I'll start by designing the side of part B right in here, because that's going to define the shape of everything. And then I'll do a flange for the top coming out right here, and then we'll come in and we'll start building a piece that will come in and become part A. So we'll probably build this B, A, C or something like that as we go through here. So anyway, just a good idea to stop and think about what you're going to do. If you have a different plan for how you want to make this, different sizes, different shapes, take the principles of this design and create your own in here. There is also quite the possibility that you could design this by doing as we did in with a 3D printed part, by printing this out, shelling it, and taking a side out from the outside. And then as you go to unfold this, you could just pick different edges to separate this along as you come to do your sheet metal layout. There's all sorts of tools, all sorts of ways to think about your design. Like I say, just as there's many ways to manufacture a part like this in the real world, there's many different ways to design it in Fusion 360. And while some of them are wrong, a lot of them are right. Okay. So we're in the drawing mode right here. We can get out of the drawing mode. And so I'm just going to close that drawing. That's drawing has served its purpose, and I don't need this part of the arm anymore either, because I'm actually going to be neglecting this whole thing for a little bit. I am actually just going to start a new design. Okay, and again, just as with the previous part, even if your arm's a little bit behind, and your linkages aren't all working properly, don't worry about it. You can build the bucket from first principles, and we're going to make it out of sheet metal right here. So, okay, well, what are we going to need to do? We're going to need to create a sketch. And I'm just going to pick a plane right in here. And that sketch is going to be the side profile for my bucket. And I really do enjoy Fusion in that I don't have to, get any dimensions or angles or anything right. I just go ahead and design something like that. And who cares if it's right or not? Okay. Because what we're going to do now is we're going to come along and we're going to provide some dimensions. And why is that dimension? What's that little piece doing right in there? Okay, Fusion 360 is messing with me. That should be just a single continuous line along the top right there. I'm just going to delete that, and see what happened there. Must have had too much coffee and clicked my mouse button too soon. Okay, there we go. And this one right in here is telling you that that's a horizontal line, which is good. We do want some constraints on this design. Let's come in here, pull in a dimension right here, and based on my drawing in there, I think I want that to be about 50 millimeters long. Okay, and then down on the front, I said I wanted this side to be about 70, and you'll notice depending on where I put that, it will either give me an aligned dimension or a vertical dimension. I think I'll go with the aligned along the front, and then I thought each of these sides could be somewhere around 30. And yeah, that messed it up, but don't worry, we'll fix that up in just a moment. And there's no magic to these dimensions that I've got right in here. Okay, now I'm going to crank this front piece out on an angle a little bit. Right now it's less than 90. We originally had that out at about 120. Let's see what that looks like right in here. And we get funny dimensions when we come along here. But let's play with that. I think maybe 100. 110. 105 might look good for the front. I don't know. It's your bucket. You decide how you want to design it. Again, this is one of those things where you'll have to test it. And we probably want this out at a little bigger angle in here. Let's try 100 on there and see what we get. That's looking a little nicer. And then this piece right here, I think I wanted that. Actually, instead of telling it that I'm going to put a dimension on there, I'm just going to make that go horizontal. There, it was already selected, so when I clicked on the horizontal constraint, it just made that horizontal right along the bottom. And then I can dimension this angle right in here. And that's telling me, let's make it 150. And then just to wrap that up, I think this is going to tell me that this is an over-constrained dimension. So I'm not going to put a dimension in right there because this angle and this angle are controlled by these lengths and dimensions that we've got right along here. It knows if this one's horizontal, and this is all in here, we've got this all fixed, and that's looking really good. Okay, so that's going to be the profile of our bucket, and I'm going to finish that sketch. And then I'm going to take that and I'm going to extrude it. And what I'm going to do is I'm going to extrude it as a new component. And I am going to extrude it 1 millimeter because most of the sheet aluminum I have kicking around the shop is about 1 millimeter thick. There we go. Now we've got this 1 millimeter thick piece sitting right in here. Now what I want to do is I want to convert that to sheet metal. And in here under create, we can go convert to sheet metal. And I'm just going to pick that component and tell it that I'm going to make it into aluminum 1 millimeter thick. Now, if you don't have an aluminum setting in here for 1 millimeter thick aluminum, You probably do because we used aluminum in an earlier tutorial, but you can come in here to your library and you can click on an existing material. Um, let's see, well, where did we find to go in and do that? It is covered in a previous tutorial, the one where we made the control box. So you can go in there and you can edit this up and just pick 1 millimeter thick aluminum factor, and we can fix that up later on if we need to. And now this has turned this into a 1 millimeter thick piece of aluminum. And I am going to create a flange, and said flange is going to come off the top side right here. Actually, I guess it doesn't matter so much which way it comes, but I'm going to put it right there. And I want that to come out. Oh, let's make it come out about 30 millimeters right there. Now we are going to end up mirroring this part and putting it over onto the other side. But for right now, we're just going to build half of this, and then we can tweak and play around with it later on. 66 centimeters wide. I'm going to go 35, make it a 70 millimeter wide bucket. Could go wider if we wanted to scoop up a little bit more. Could go narrower if we wanted a little more precision to fit into the corner. We could have a different angle on here. It doesn't have to be 90 degrees. It could be 100 right here if you wanted this to be a little bit tapered for fitting into the corners better, or it could be 80 if you wanted it to be a little bit wider for not fitting into the corners. But you know what? 90 degrees is a nice easy bend. And one of the nice things about doing this in sheet metal is you can see that it actually turns that radius in there. Now also keep in mind that when you're turning that radius, that it's measuring on that line. In this case, if we look at that face right there, it's measuring from the inside of your sheet metal to, should only be measuring to that end right there. So just keep an eye on that. Is controlled by your height datum, and right here, so you could go to the outer faces, and then it should have that arrow come out to this side, and your bend position can be inside, outside. So you've got some different parameters that you can use to adjust, and we're going to use those helpfully later on when it comes time to create our flanges. Okay, and we put that along the full edge for 35. That looks good. I click OK, and now I've got one sheet metal part. Now what we need to do is we need to create a sheet metal part that's going to come down around the back right here. So what I'm going to do is I am going to create a sketch that's going to come right in here on this back, and let's just create a sketch that comes in, and I'm just going to put it on this plane right there. Okay, and it's just going to be a rectangle. And actually what we may want to do before we put that rectangle in is let's just project this sheet metal edge into the drawing. Okay, and now let's create a rectangle from this corner down to that corner, and there's our 35 millimeters right there, and we will finish that sketch. And so you can see we're going to have a piece of sheet metal coming right in there, and that's going to come right out to that edge. And so what we're going to do right now is we are going to take that piece and we are going to extrude that. I got to go back to my solid tools, extrude this by 1 millimeter. And I'm going to create that as a new component again. Okay. And then I am going to convert this piece into sheet metal. So back to our sheet metal tools, create, convert to sheet metal, and again, aluminum 1 millimeter. There we go. Now that it knows this is a piece of sheet metal, we can come and add it right down in here, and we can put a flange coming off the bottom. Okay, and let's make that flange. We know it's going to be about 30 long, but it's not at 90 degrees. Okay, that angle will be less than 90. What did we say? 80, 70, is that a 75? Let's see right in here. Now this is where we want to watch where our dimensions are. I think we want a dimension to the outside right there on that curve because we want to make sure that we come out and around this corner right here. Now it may be necessary that we put a radius on this corner to fit on the inside of our sheet metal, but that one's not quite coming out at 75 degrees. So if we need to find that exact angle that we want to have that bend come at, just come back into component 1, come into your bodies, body 1, sorry, maybe that's under sketch. That was in sketch 1. And I'm just going to click OK on that for now. I want to take a look at sketch 1, and we can do a dimension on here. 107 degrees. That's why I was having a hard time finding the right dimension. Okay, finish the sketch. Escape gets us out of there. We didn't change anything. And in here, under component 2, and aluminum component 2, there's body right in here. We're building that up. And we had an edge flange in here. We want to edit that up. And so 107 degrees, we're working at this from the other side right now. I'm just going to turn on my component color cycling so I can see these things a little bit better. Makes that stand out really nice. And 180 minus 107 is going to give me, what's that, 70, 180 minus 107 is 80 minus 7 is 73 degrees. So we just measured that right there, and now you can see that's lining up right around there, and it's coming around the outside nicely. Good. Okay, now let's do an OK on that. We've got that in there. So now we'll probably want to come back and fillet these corners just a little bit in our original drawing, just something to keep in mind. But let's come in and create another flange since we're in flange creating mode. And here we go. This one, we also set it to be 30. So we'll take that out 30. And I think this was a 100 degree angle. So let's try, so that would have been 90. 10's not enough. There we go. That must have been a 150 degree angle in there before. And that comes up right around there. And I'll click on OK. And let's put a flange right in here. And this is also going to be 30 again. If you had different measurements, you could come in and figure that all out. But instead of being at 90 degrees, this is going to be 40. Is this at 30 as well? There we go. And that comes through. And that piece of sheet metal, if we bend it absolutely perfectly, is going to come through and meet right at that location. And that looks beautiful. That's going to form the back and come right all the way around here over top of everything. Beautiful. Now we just need to create some flanges on here. So I'm going to say, okay. Now this is the tricky part where sheet metal gets interesting. Let's come in here and we want to flange here, 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 and here. So we've got all those flanges coming inwards, and let's just bring them in. Oh, sorry, picked the wrong thing. Cancel that. Those two parts are so close together. To make this work, what I'm going to do is I am going to temporarily hide the first component. So that sheet metal part right there, I just want to take a look at these parts right here. And let's put our flange on right here. Okay, there we go. Now I can unhide that first component so I see how it all comes together. And let's try a height of 10. And now we've got a problem that everything's kind of overlapped right in there. So let's try our bend position. If we move it to inside, that will have that all bend up and it will tuck on the inside of this piece, which is kind of nice, but it leaves that sharp edge exposed there. I'd like to see if we can get that. What happens if we go tangent to bend? No, outer faces. Adjacent, there we go. That comes in, wraps that right around there. And what you'll notice is that it's smart enough to know that right in here, it needs to leave some gaps. So when it makes those flanges, that it doesn't start bending into itself. So when we go to lay everything out and to create our flat pattern components from this, it's going to come out pretty nicely. So there we go. There's half of a bucket right there coming together. And if you want the bends on the inside, you can put them on the inside too. That might give you a little cleaner look from the outside. I don't know why I thought I wanted them on the outside. Like I say, there's many different ways that you can assemble this and make it work together and have it come out really nicely. If you wanted right up here, you could add another flange and tuck it in underneath here and have a couple pop rivets come down from the top so that it's all tightly sealed on the inside. So, okay, that's looking pretty good to me. And now we just need a way to mount this onto our arm. So here's our sheet metal part right now. I think we're going to put a new sheet metal part right onto the top and we're going to pop rivet it down there. So let's come back to create a sketch. Let's create a sketch onto this face right here. And we'll project this surface, so we've got that to refer to. We'll say, okay, now we've got that surface in there. Then let's pick something that's going to run not all the way along, but almost all the way along, right in here. And there we go. It doesn't show up all that well because of the color cycling that we've got turned on, but we can still dimension it a little bit. And so let's come in here and we will dimension it this side right here. This is going to tell us how it meets up with the inside of our arm. So again, if you've forgotten that, you can come take a look in here. You can go and say, okay, I'm going to do an inspect. And I'm just going to measure from right there over to right there. And our internal dimensions 38 millimeters. So this is going to be half of 38 millimeters, which doing math in my head, 19. Okay, so that's going to come up to 19 right there. We are going to check when we do all of our folds to make sure that that is the right size. But right now we can dimension how far back do we want it from the front. Pick up my dimension. We want to dimension this distance. New dimension. Escape. Quit dimensioning the wrong thing. Want to dimension that line to that line. There we go. And let's set that back just a few millimeters from the front. And then we know based on our original sketch that we want at least 40 millimeters between our hole. So we probably want this side to be 50 millimeters long. Would 50 be long enough? Because it's 40 from middle of hole to middle of hole. So yeah, we want that to be 50 millimeters long. That's going to be longer than this, so maybe we set that down to 0. Doesn't like it when I give it 0 as a dimension. We'll just set it back from the front by 1, and we can shorten this down to 48. It'll still work fine. There we go. That looks pretty nice. Okay, so again, finish your sketch right on here, and let's come back to solid. We'll do an extrude. Take this piece, extrude it by 1 millimeter, create a new component. Okay, and now we've got that piece sitting right on there. Come back to our sheet metal, convert that into a sheet metal part of 1 millimeter thick. Okay, and now we can create a flange coming up from right here so that this can come up and touch. Okay, now like I say, we just want to remember that this bend position was on the inside right there, so that we're at our 38 on the outside. So that's looking pretty good coming right up in there. And I'd say we've got half of our bucket right now. Okay, so looking pretty good right on here. And now what we're going to do is we're going to add a few features. Oh, sorry, it's 20 millimeters to that hole. I just should have extruded that a little bit longer, so I'm going to come into this flange right here, and I should have made that, it's going to be 20 to the center, so 2 on the top. Let's go 25. Beauty. Okay, so now we need to put some pop rivets and holes in here for holding everything together. So typical pop rivets we have in the shop are 1/8 inch diameter or 3 millimeter pop rivets. So we need some 3 millimeter holes inside here. Probably put a couple right through here. So we can come in here and we can come in here, and there is a way to put some holes in here. We'll do that in the solid mode then. Come in here and we're going to create a hole on this surface. That's a little bit bigger than we need. So on our hole tool, we can tell it we want it to be 3 millimeters in diameter. Okay, knows which face it's going to be on. We'll pick a reference side right in here, and we'll pick right there. We'll pick right there, and let's set it in 10 millimeters from the edge. And we'll set it in. We want to leave enough space right in here so that our pop riveter can get in there. So let's set that only 7 millimeters. Again, this is going to get mirrored over onto this side. We'll put another hole on the back right here. Okay, it remembers that it was 3 millimeters. We pick our 2 sides, and we'll say 10 millimeters. And reference 2, we'll pick that side, and we said 7 millimeters. Okay, that goes right through there, a couple of pop rivet holes. We're also going to need a couple of holes up here for mounting this onto our robot arm. Now those are going to be 4 millimeter diameter holes, so let's pop a hole in on this surface right here. Okay, and so we up this to a 4 millimeter to fit that number 8 screw, and just careful which reference edges you pick. We're going to pick that edge, that edge. We'll set that back. They've got to be fairly close together because we need to the edge, because we need to space them apart by about 40 millimeters. So let's say this one is going to be 8 millimeters back, might be closer to 6 millimeters back from the edge right there. And actually our second reference, I want to undo that reference. I want to select a different reference right here. I got rid of the wrong things. I'm going to select a reference right here. There we go. Leave that one at 6 for now. and the second reference I'll select down right here, and let's bring that, we want it up about 20 from the bottom. Now there is that bend right in there that brings that up 2 millimeters extra, but let's make it 18. I think that'll look a little bit nicer, and it'll let us radius that corner a little more closely in line with what's going on right there. But we've got a few other things to play with first. So there we go. There's one 4 millimeter hole. Let's create another one on this surface down here. And the first reference that we want is from the center of that hole. Create a hole on here. It's 4 millimeters. Reference one from the center of this hole. It's still trying to create that. Okay, well, we'll come in here and we'll figure out how to dimension this one exactly the way we want in just a minute. Let's measure from the front right back to there. We made that 6 back for the first one. This one then would be 46 back. And then we'll take the second dimension right down here, and we made that 18. Okay, and now I'm not quite liking how that sits right on the end, so I'm going to come back and find this hole, and that first one, I'm going to take that down to 4 millimeters. And the second one, then if I want a difference of 40 between them, I'll take that down to 44. They're sitting in there reasonably nicely. Now, if you wanted to get really fancy, you could use the rectangular pattern, and you could put a pattern of holes right along here, and you could pre-hole punch a whole bunch of different holes at different spaces right in here, so you could adjust different lengths when you're actually using your arm. Or you could just try popping a few holes in with a hole punch once you're done. Anyway, there we go. We've got some holes mounted right in there, and that's going to enable us to mount this to our arm. I think while we're doing that, let's come over to our sheet metal, and it's got a fillet command, and let's just fillet off this corner of our sheet metal right there, and let's take that to, I don't know, a 6 millimeter radius. Okay, and in fact, we can add, let's add another edge right there. Also, we'll put that one up to a 6 millimeter radius. And then we've got those two sides because we don't want to have sharp corners, poking around and scratching people. That's just poor sheet metal design. Okay, there we go. That's looking like a part that we could mount onto the top right there. We'll add a couple more holes along here. And so we'll come back to solid, hole, pick something right there, 3 millimeters diameter again. Okay, reference edge. Zoom in a little bit right here, select a reference edge. 1, and let's drag, we didn't want to drag that. We want to drag that down right there. I dragged the wrong thing. I changed the diameter, set it back to 3, select this reference edge right there, and we'll bring that in. Let's see what's going to be nicely radiused. We can probably do that 3 millimeters from the corner, and then we'll make it 3 millimeters. Wasn't where I wanted it. Thankfully we can undo that. There we go. We'll put it down there. Reference 1 from that edge, 3 millimeters. Reference 2 from this edge, 3 millimeters. There we go. And that hole punches all the way right through both those parts. Let's put another one in right down here. Put it in here somewhere so that when we dimension it, it stays where we want it. And we'll dimension it from this edge. And we'll put that in 3 millimeters. And then from that edge, I'll make it stand back 3 millimeters as well. It's getting pretty close to the edge in there. Pop rivet head might stand out too far, in fact, and might sit over the edge. Let's go back 4 and 4. Yeah, I think that should work pretty nicely. Looks like we've got room for a pop rivet head to fit on the inside in there. Let's fix that previous hole so it comes back 4 and 4 as well. Yeah, that looks nicer. And as you can see, I'm pretty much just playing at this point because we've already got a couple of different designs on here. But as you get going with Fusion, it is kind of fun to play with it and say, I can do all these different things, and it doesn't matter if I don't get it absolutely perfectly right the first time. Oh, this one I actually wanted to be a little further along from that edge because I was only going to put one pop rivet in here. Let's put that hole in right about right here. Drag it up somewhere in here. We want that to come right through at the center of this piece right here. So let's add a dimension right here. So we'll reference that to be 4 millimeters in. Okay, and then our reference right here, let's see, where do we have a nice straight edge to reference a side? It's going to be a little bit trickier. Ideally, okay, I am going to select a reference right here, and let's see, can I'm having a heck of a time picking up a corner. I wanted to be able to get a corner in there, but we'll just take that and let's see what happens if I tell it we want that to be 10. Can we bring this back to 4? Is that going to conflict? Yeah, that's pretty good. Right in there. And then we'll come in here and we'll put a hole on that face. Reference edge 1 is going to be right up here. We're going to make that to 4. Reference edge 2. Make that to, I think we did 10 last time. Why does that tell me that shrunk down to 4, 3? We want that to be at 4. Yeah. It's going to work fine right there. Just something to hold that little flange in. In fact, that one's probably not critical that we pop rivet it in place, but you can play around with it a little bit later on and get it exactly where you want it. Right in here, 4, and I think we did 4 on one of those before. And then we'll put 2 pop rivets in here just because it's down at the bottom and because the pop riveter is fun to use. Just drag that in a little bit, and then we can select a reference and go 4, and select the next reference and go 4. That's looking pretty good. Okay, now, once again, I don't like having sharp corners on sheet metal anywhere, so we're going to take these corners right in here. We're going to come back to our sheet metal tools. We'll do a fillet on this corner, and we'll do a fillet on this corner right down here. I guess we could do a chamfer, that's easier to cut, but either way, we've got 2 of them on there, and 4 millimeter radius around there. Just reminds us to file those corners off, round them off nicely, and we should be good. Don't have to worry about those ones so much because they'll all be tucked in and out of the way. Okay, there we go. We've got half of the structure all put together. Well, you'll remember what we've done in the past when we've had half of a structure put together is that we go ahead and we do a mirror. Okay, so what do we want? Well, we want mirror components. 1, 2, 3 components are going to get mirrored, and our mirror plane right here is going to be that seam like so. And there we go. We've now got a mirrored part right here. There is our bucket, able to come in and scoop things up. You could play with the dimensions, build yours the way that you want. This is just some suggestions and some thoughts on if you want to make it out of sheet metal, how you could do that. Now, right now we want to turn these into single components. So come back to our solids and we go combine 1 and 2. We're going to join those together. Okay, combine 1 and 2, join those together, and combine 2, join those two together. And so now you've got all your parts sitting right in here. So what we'd like to do now is get some flat panel drawings for this so that we can print those out and take them into the metal shop, put them on a piece of sheet metal, and use that as our template for punching all of this out. We could also take them to a plasma cutter, water jet, laser cutter, whatever cutting machine you want, and we could definitely cut them out from right there too. So if we come into our sheet metal tools, we can come in here and we've got all our rules set up. And here we go, we've got create flat pattern. And just pick the stationary face of what it is that you want to create and say OK. And there is a flat pattern for that part. We can turn off our component color cycling tools on there. And if we finish that flat pattern, returns the folded model. Before we do that, let's print that out. Okay, and so we come in here to drawing, from design. Oh, we've got to save this part. So let's save it as sheet metal bucket. Should have done that right from the beginning. New drawing on A4 paper. Say OK. Takes a moment for it to think that through. And there is our base view. And we say OK. And there you go. It's got your bend lines right down the middle, your allowances, shows you where to put all the holes. You can come in here and add your dimensions on here so you remember which size to punch which holes. Dimensions. Let's see right there. That's not what we wanted. There we go, radius 4. Oh, sorry, diameter 4. Place that. Place that right in there. And that should tell you pretty much everything you need to know about your part. But just to help somebody who goes to make this, we want the dimension between here and here. And the dimension between here and here. And you're saying, oh, there's some weird numbers showing up right in here. Well, don't forget, it's taken account the bend radius right in there. So you might want to dimension your bend line right in there as well. And depending which end you're bending from, maybe you I didn't leave myself quite enough space there. Put that up at the top. Not good dimensioning practice right there necessarily. Let's put some center holes for our circles. Just makes them easier to punch with a hole punch. And there you go. That part is going to be available to print, and you hit your PDF or you send that out to your printer. You take that into the shop, just glue it down onto a piece of sheet metal, punch, 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 bend, bend. You've got your part. Remember to round off the corners nicely when you cut them out. Okay, let's come back to our sheet metal bucket right now. We're going to finish that part of the flat pattern. Let's come in here and take this part of the flat pattern. So come in here and sheet metal tools and create flat pattern, and our stationary face for this one, we'll look at it from this side right here. Okay, and there is our bent out part right in there with all the holes in the right places. And so let's come in here and create a drawing from the design of this part. And we'll put it on the A4. Let's go for the wider A4 paper this time so that it fits a little nicer. And oh yeah, make sure our scale is 1:1. There we go. Now there should be a way to rotate that drawing viewpoint, but I'm not too worried about that. And you can go through, center mark your holes, and do whatever you need to get that part to come out the way that you want. And it looks like all of these edges are big enough that you can probably find a way to cut them on shears. Okay, the final part that we're going to need on here, let's come back to our sheet metal bucket right over here. We'll finish that flat pattern, is going to be this outside part right here. So we're going to create a flat pattern. We'll use that surface as our flat surface. Oh, it didn't like that. What happened right there? Let's undo that, go back. Shouldn't complain at us like that. Oh. What's that warning showing up down there? Flat pattern 1 is giving us grief. We'll try attacking that flat pattern from a different point of view. Great flat pattern. Let's take a look at it from this side. Oh, it's giving us an error. Let's undo that again. Sometimes it'll give you that if it doesn't know how to create the flat pattern, but there's no reason it shouldn't know how to create that flat pattern. Let's just turn off a couple of those other components for right now. We'll make them invisible. Oh, why are things not turning invisible for me in here? Those are all our mirrored parts. Component 3.1. Okay, that's in there, so we know which one that is. Let's go back to turn this on. Component color cycling. I want this green part right here. I'm going to turn off these other components just so that I'm not accidentally picking anything else up by mistake. There we go. Maybe I was only picking up part of the mirrored part or something in there. So if you're having problems, again, turn on your color cycling and come in here and turn off the things that you don't need. You can just hide them by clicking on their visibility, kind of like layers in AutoCAD. Okay, create flat pattern, stationary face. Okay. More info. What's it doing wrong? It's not giving me any info on it. Strangely, I had a very similar shape done up earlier, and it was working out beautifully. Create flat pattern. Maybe it'll be happier if I pick something in the middle. It is really being nasty to me. Those other ones created so nicely. And there is nothing wrong in here that says that should not be able to form a flat pattern. That should be fairly easy to create as a flat pattern, in fact. What's going on in here? Okay, if I turn that off, component 3, mirror 1, 2, 3. Okay, so those parts were the mirrors, and they just got combined right into here. Component 2, 1. There's component 3. Component 2 is that part right there, which makes sense. Should have given them names, of course, as we come along in here. And let's see, all of the parts for that. Let's come in here and let's just double click on that. Make this one the active component. And so I just turn that dot on so I can see its entire assembly timeline right there. And that all looks like it should make sense. And create flat pattern. Pick a different face. And it should be giving me the error info down in that corner to tell me what's going wrong and why it's not working. And it just does not want to create that flat pattern for some reason. Well, we do have a couple of hacks and workarounds on that. And in this timeline right here, let's go back before we mirrored it. Okay, let's see if we can create the flat pattern of half of it, and then we can always just duplicate that. It does not want to do that. Okay, well, a little disappointed in Fusion 360's flat paneling for me on this one right here. I'm sure that somewhere out in Fusion 360 land, somebody's going to say, oh yeah, you've just clicked on the wrong thing right here. You can create a flat panel for that. And in fact, I expect your drawing is probably going to create that flat panel just fine. But I'm having problems with the sheet metal tools right now. I'm going to post this and let you work your way through that because I think there's going to be a solution to this, and yours is probably going to work out a-okay when you go ahead to create that flat pattern. It's a weird problem that I've clicked on something, and you know, I've been editing most of those out as we go along, but now that you're getting into Fusion 360, I think it's fair enough for you to know that I run into problems with it from time to time too, and I have to go back and sort them all out. So anyway, very cool way to go about creating flat panels for your parts, and then you can come back and you can see them all assembled. And what you can do now, of course, that you've got this all assembled is let's turn everybody back on here. Component 1 is back on, component 2, component 3. We've got everybody back on there. Come back up here, activate the entire project, save this file. Okay, and now that you've got that assembled, you can come over to your arm. You can drag your new sheet metal bucket into right here. Drag it over here somewhere so you can see it. Say OK. And then you find the hole. This hole right here is going to match up to that hole right there on the inside. So go ahead and assemble that. And let's capture that position. Okay, careful to pick this hole on the outside surface right there. And then, no, not right there. Cancel that. For some reason, my 3D mouse is taking a moment to respawn. There we go. You get hooked on those things, and when they don't work, capture position. I think that was just a little bit of lag actually as my computer was doing something else. So there is one hole right there, and that is going to come over and fit onto that hole right there. Flip that around. And that's looking promising right now. We want our motion to be revolute. And I forgot the first step that we had to do before. Undo what we've just done. Come back over here. And what we need to do is we need to take a look in here and move that out of the way. And our sheet metal bucket, we have to remind that it is going to be a rigid group. Capture that position. And now we can come in here. And with this being a rigid group, when I move the first part, everything all moves together. So create that joint. Right there. To get in here and rotate this about just a little bit. So I can see into that arm right there. I'm in hole mode. Did I click on hole instead of joint? Okay. Joint. I think I need more coffee this morning. That joint right there. It's going to come in, meet up with that surface right over there. It's flipped around backwards. It's a revolute joint. Let's take a look at that. That's looking okay. There is our bucket all the way over there. And now we can take that joint right in here. And this joint that we just put in here is the bucket to arm. Okay. And what we want to do is we want to drive that joint to put it into a more rational position. Somewhere right in there looks good. You can take a look at this from the side. From the top, make sure that we don't have any conflict between parts. Everything fits in there really nicely. Drive that in. It will come in about that far. It's looking good. We can see. Oh, I put it to the wrong hole. Oh no, that's the right hole. Let's see, we're not conflicting right up there. Don't have any interference. Both our holes align properly. I bring it like that. We can see through both the holes, so we can run something right through there. Okay, now it's just a matter. You add your linkage in here and your 10 milliliter syringe, and you have a fully functioning arm.